Hello everyone and welcome to our 49th episode. Today we're talking about the day our app, Dify, first went live. We were so excited, ready to see our hard work pay off. And then it crashed. The first wave of users came in and boom, everything went down. It was a brutal but incredibly valuable lesson. The very first thing we learned from going live wasn't about features or marketing, it was about capacity. What is capacity? It's the single most important concept you need to grasp when you launch a product. Today, we'll dive into what that really means using a simple analogy, freight cost. We'll explore capacity, bottlenecks, and the crushing force of concurrency pressure. This isn't just a technical story. It's the foundation of building something that can actually handle success. So, if you're building anything, stick around. This is the lesson you don't want to learn the hard way. Let's try to visualize what capacity actually is. Imagine our app is a massive logistics warehouse. The users trying to access our service are like trucks arriving to pick up or drop off goods. The capacity of our system is like the number of loading docks at this warehouse. If we have 10 docks, we can service 10 trucks at the same time. This is our concurrent processing power. If 11 trucks show up, one has to wait. It forms a queue. Now, let's talk about the bottleneck. Imagine the single road leading into our warehouse has only one lane. Even if we have 100 loading docks, only one truck can pass through that road at a time. That single lane is our bottleneck. It doesn't matter how efficient our warehouse is. The entire system's performance is limited by its narrowest part. In a software system, this bottleneck could be anything: a slow database query, a limited third-party API, or insufficient network bandwidth. So what happens during a crash? Picture this: it's Black Friday. Hundreds of trucks are suddenly heading for our warehouse. The single-lane road gets completely jammed. The queue of waiting trucks spills out onto the main highway, causing a massive traffic jam that paralyzes everything. In our system, this is what happened. The number of user requests, the trucks far exceeded what our single-lane road, our bottleneck, could handle. The queue of waiting requests grew so long that it used up all the system's memory, the waiting area. When that waiting area is full, the system has no choice but to start turning away new trucks. For users, this looks like a timeout, an error message, or just a frozen screen. The system has crashed. It's not a slow decline. It's a sudden, catastrophic failure once that limit is hit. So how do we fix this? The obvious answer is to scale up. In our analogy, that means adding more lanes to the road or building more loading docks. In tech terms, this is called horizontal or vertical scaling, adding more servers or more powerful servers. But it's not always that simple. You have to find the right bottleneck first. This brings us to the core insight about system performance. Every system has a throughput limit. Throughput is the number of trucks our warehouse can successfully handle per hour. You can't just process an infinite number of requests. There is always a hard ceiling. And here's the really tricky part. The relationship between load and latency is not linear. Latency is the time it takes for one truck to get through the whole process, from arriving to leaving. When the system is running well below its capacity, say at 50%, adding a few more trucks barely affects the time each one takes. The latency stays low and stable. But as you get closer to that throughput limit, maybe 80% or 90% capacity, things change dramatically. Adding just one more truck doesn't just add a little bit of delay. It can cause a massive spike in latency for everyone. This is non-linear latency. The queue starts backing up exponentially. Your response time might go from 200 milliseconds to 5 seconds and then to 30 seconds in the blink of an eye. And then you hit the wall. The system doesn't just get slower. It stops working entirely. This is why crashes often feel so sudden. 1 minute everything seems fine, maybe a little sluggish. The next minute, total failure. The system was pushed just past its breaking point and the non-linear latency curve went vertical. Understanding this tipping point is crucial for building resilient systems. You need to monitor your resource usage and know where that cliff edge is before you go over it. Now, let's think about that moment of crisis. The system is down, users are frustrated, and your first instinct is to tell them, just try again, refresh the page. It makes sense, right? If the request failed, maybe the second or third try will get through. This is the retry dilemma. Let's go back to our warehouse. A truck tried to place an order, but the system crashed. The driver hits retry. But what if the first request actually made it through to the database just before the crash, but the confirmation message never made it back to the user? When the user retries, are they going to place the same order a second time? Suddenly, the customer has been charged twice for the same item. This is a huge problem. How do you design a system where retrying is safe? How can you ensure that a repeated action doesn't lead to duplicate data or duplicate charges? This opens up a whole new world of challenges, concepts like idempotency and the complexities of distributed transactions. We managed to fix our initial crash by scaling up our capacity, but this retry problem was the next big monster we had to face. And it's a fascinating topic that we'll explore in depth in a future episode. So make sure you're subscribed so you don't miss it. Thanks for watching, and I'll see you in the next one.